Okay, these are the 2008 multiple choice A-B test, part B, starting with calculator problems, or you may use a calculator on some of these, but again, some you don't. And number 76, the graph of f prime, the derivative, is shown for the interval from -2 until we get to 5. Okay, what intervals is f increasing? Now remember, what's from our textbook, if the derivative is greater than 0 on the open interval, AB, then we say that f is increasing on AB. If it is less than 0, if the derivative is less than 0 on the open interval, we say it's decreasing on the closed interval. So that was a notation thing we talked about. So we look over here, this is my derivative, so it is positive from -2 to 1, okay? And it is positive from 1 to 3. So on these open intervals, I could have written that down also. Okay. So you can see here by the graph that f prime of x is greater than 0 on the open interval -2 to 1. And f prime of x is greater than 0 on the open interval from 1 to 3. Now right at these points 1 and 3, and it's 0, so not greater than. All right? Okay, but since this is the case, we say that it's increasing on this interval, and since this is the case, we say it's increasing on this interval. All right? But if we take the union of those two intervals, since 1 is in both, we can just say that that's basically the same as going from -2 to 3. I didn't see this as one of my possibilities, but I did see this, so this was my selection. Okay? So remember that for increasing. If the derivative is greater than 0 on the open interval, we say it's increasing on the closed interval. Hope that makes sense. Okay, number 77. Alrighty. The figure above shows a graph of f with a domain between 0 and 4. X is between 0 and 4. Which of the following statements are true? The limit as f of x approaches 2 from the left, does that exist? Yes, here's 2. As I approach 2 from the left, it does exist, whatever that, it's approaching that point. And the limit as x approaches 2 from the right, from the positive direction, does that exist? Yes, that does exist. So that's true. We do have a left limit, whatever that vertical position is, and we do have a right limit. Okay. Does the limit as x approaches 2 exist? No, because the left limit has got to equal the right limit, and those aren't the same. So just 1 and 2 are true, so 1 and 2 would be letter C. So it's just a good limit question there. Hope that makes sense. We can zoom in a little bit on this, I think. All right. And then number 78. The first derivative of the function is defined by f prime of x equals x cubed minus x. On what intervals is f increasing? So that's the derivative. So we just want to know whenever the derivative is positive. All right? So we can do this by calculators. Let's get our calculators out. Zoom out a little bit here so you can see all this stuff going on here. And just graph it and find out when the derivative is positive. What intervals? So y1 will put the sign, and that's going to be x cubed. Remember, make sure you're in radians. X, math 3 gives us the cube, minus x, parentheses. And we want to graph this between 0 and 2, so we can use, I guess, zoom 4. That should work out okay. Yeah, that's kind of a lot of junk going on there. Let me change the window. Go to my window, and I'll go from, let's see, we want to go from 0 to 2, so I'll go from -1 to 3. Oops. -1 down to 3. How's that? That'd be a little bit better. Graph that. Okay, so we're just interested in when the derivative between, this looks like this is 2 over here, so that we want to make sure that we're just going to check to see where it's above, okay? Because the question is on what intervals is f increasing, so that's increasing whenever the derivative is positive. Okay? And you can see that I'm going to be going over here, and then you see my x value is going to be 2 right there. That's greater than 2, so this is all I'm interested in, is this area over here. Right there, that little part there, that's the only time when the derivative is positive. Okay? So let's find the interval. So let's check that 0, first of all. So we go second calculate, and we'll go to 0, enter. And left bound, that's okay, good there, enter. And the right bound, enter, and see what that is. And that happens to be 1. Well, that's easy to remember, I don't have to worry about that. So that interval, the left bound will be 1. And let's try the right bound, 0, that's 2. Let's go over here. Oops, there's my left bound. You can see that. And go down to the right bound, or like that, that's better. Enter. And I get 1.69. So let's take a look over here. So I'm between 1 and 1.69. And it looks like that's right over here. Between 1 and 1.691. All right. And that's where the derivative is greater than 0 on the open interval, 1 to 1.69. So that means we say it's increasing on the closed interval. Okay? So we could say by the calculator, we know that f prime of x is greater than 0 on the open interval, 1, 1.691. So we say it's increasing on the closed interval. Okay, if that helps. Okay, the next one would be number 80. Oh, the other side, excuse me. Number 79. Let's zoom in on this a little bit. Okay. And what we got here is we've got this, just properties of integrals. If the integral from -5 to 2 equals -17, and 5 to 2 equals -4, what is the value of the integral from -5 to 5 of f of x? All right. So we know that we can break this up. This is one of our properties of integrals. So the integral from -5 to 5 of f of x is equal to the integral from -5 to 2 plus the integral from 2 to 5, because that's what we got. We got 2's and 5's here. Okay? Okay, but we're actually not given 2 to 5. We're given 5 to 2. So we know that if the integral from 5 to 2 equals -4, I can reverse those. I couldn't do that anyway because the 2's got to be smaller than the lower limit must be smaller than the upper limit, or to the left. So I'd have to reverse those anyway. So if I reverse those and rewrite this as 2 to 5, what do I do with this? I make this negative, which makes that positive. So I put a negative here and make that a positive, and that's going to give me this. Okay, so we have to reverse that. I hope that's clear. So this integral from 2 to 5 will now be +4, so I've got -17 plus 4 is -13. All right? Now, if you didn't reverse that, you would have put -4, that would be -21, so that's our distractor, you see. Okay, is that okay? All right, and then number 80. Okay, now be careful on this one. Number 80 is a little tricky. How many points of inflection? So you're given the derivative of the function. Okay, how many points of inflection does the graph of f have on the open interval? Okay, I didn't read this carefully, and I put 2 because 2 was the number of critical points, or a number of changes. We actually just did the second to the derivative, actually. So you got to be careful. I just found the number of extrema, maximum or minimum. So you have to make sure that you're talking about the points of inflection, so you need the second derivative, all right? So points of inflection will be when, actually we should state that too. F double prime of x equals 0 and changes signs. Okay, that's what we want, because we want concavity to change there, all right? So that's what we're looking for, so be careful, because I kind of jumped the gun. I was thinking extrema, and that's one of your possible answers. So let's see how we're going to do this. So I have to zoom out a little bit here so you can see what's going on. And we're going to put this now this is the derivative. This is f prime of x, so we'll put this in y1. That's going to be x squared cosine x squared parentheses, all right? But we're not that interested in y in the first derivative. We're interested in the second derivative, so we have to want to look at the graph to see when we have sign changes and where we have zeros. So we'll go down here and we'll just take the derivative of this, and you can do this on the graph, and all you have to do is math 8, like we take a derivative, math 8. Okay, and then we're going to put y1 in there, so we'll just var, y vars, enter, enter. And what you're going to do is you can take the derivative of that, comma x, and since we don't have we're just going to use it as a graph, we're not going to take a particular value, so we usually put a particular value that we want to evaluate the derivative at, but here we're just going to put x. And then we can graph that, and this is going to be on the interval -2 to 2. So I can go window, and I can make that negative 2. See what happens. Oops, I graphed both. Sorry, I forgot to turn off the other one. My bad. Now there's the second derivative. That's what we're interested in. And you can see it's going to cross 1, 2, 3, 4, 5 times. Okay? So what I'm going to do is I'm going to go back. What I should have done was I forgot to turn the first derivative off, so I turned the first derivative off. And I might make my window go a little bit out farther, so I'm going to go negative 2.5 to 2.5. That way I'll see what's going on. Now you'll see what's happening. So there's your 2, and there's your -2, and there's your 2. So we know where we're in, and you can see it's crossing 1, 2, 3, 4, and 5. So between -2 and 2, my second derivative is changing signs, negative to positive, positive to negative, negative to positive, positive to negative, negative to positive, changing signs 5 times, 1, 2, 3, 4, 5 times. So we have 5 points of inflection. Okay? That's how you would do it. Hope this helped.